Is that better?
Do I have the first page opened correctly?
Yes.
Okay. This is where you want to start.
Yeah.
All right. Indicate whether each choice is true or false. Two lines must either intersect or be parallel.
That's false, because if you have skew lines and they're on different planes.
Exactly. If they would have said two lines in the same plane must either intersect or be parallel, that would have been true. But
Yeah.
because they did not add that, that has to be false.
Mm-hmm.
Presuming that that's not to be assumed, and I can't really tell, but given the nature of the other questions, I think that he would have to say in the same plane. Okay.
Yes.
So B, in a plane, two lines perpendicular to the same line are parallel.
That's true.
Yeah. If we have two
plane.
lines that are perpendicular to the same line, like the letter pi, then these two lines have to be parallel.
It's like a transversal, right?
Yeah, exactly. That's the transversal, that right there. And these two lines, if they make 90-degree angles, then if those two angles are equal, then those lines have to be parallel.
Okay.
In space, two lines perpendicular to the same line are parallel.
False.
In space, two lines perpendicular to the same line are parallel. Let's say we have a line like that, and we have one line that's perpendicular like that, but we have another line that is in a different plane, but it's still perpendicular to that line, and these two lines are not parallel. So you're correct. That is false.
Mm-hmm.
D. Was your last test over three-dimensional geometry?
No, it was about shapes.
Okay.
Like,
Convex and concave shapes?
yeah, like mostly quads.
Okay. All right. If a line, number D, if a line is perpendicular to a plane, it is perpendicular to every line in the plane. So here's our plane. And we have a line that comes out of that and makes a right angle. So it is perpendicular to every line in the plane. Well, let's draw some other lines. There's another line. There's a line. There's a line. There's a line.
So it's false, because not all lines have to be parallel to the plane.
I think it's true. Think about how can I describe a real-life object? Take a playing card. You know what a playing card looks like?
Yeah.
Stick a popsicle stick right in the middle of it, and that popsicle stick comes straight out. So it's perpendicular to the plane. Is that popsicle stick perpendicular to that line?
No.
Well, I would say yes, but I can definitely see why you're a little confused. These kind of questions should not be directed in a first-year geometry class. I'm sorry, but I have to say that. See, I would say yes. I would say the popsicle stick coming straight out, I don't know how to draw that. We'll say that's coming straight out from the center at a 90-degree angle. Well, if I compare that popsicle stick with every other line, no matter how I draw it, it's still perpendicular to all those lines. But I don't want to get hung up on this. Not even sure I'm 100% right. But I think I am. So we'll leave that one question mark. Okay?
Okay.
Is it possible for two planes to intersect at one point?
Two planes.
Let's draw a couple of planes there. And now let's move them in space. Can we intersect them at exactly one point?
Not exactly one.
Well, how about if I draw those two planes like this? Aren't those two planes intersecting at exactly one point? They're corners? Even if you took this plane and moved it up so that you could intersect at that point, it would still be. Now, the question is are these planes infinite in both directions?
Yeah, that's what we learned.
Okay. If those planes are infinite in both directions, then yeah, that would not be true. In other words, if that goes forever in both directions, now how would I draw another plane so that it only intersected in one point? I don't think I could. I could draw a plane. This is why three-dimensional geometry is tough to teach, because it's tough to draw. In other words, this plane here intersects that plane in this line. So multiple points. But yeah, even if it was slanted. The reason I don't care for these questions is it requires you to really be able to picture three-dimensional geometry. Not that there's anything wrong with that. That's a good skill to have. It's just that's not beginning geometry. That's three-dimensional geometry. So, assuming those planes are infinite in all directions, I don't think that that could be possible. If a line is perpendicular to a line in a plane, it is perpendicular to the plane. Well, there's the plane. And no, I can't draw it like that. I got to draw it like this. And I'll make the line come out like that. And that's a right angle. So, if a line is perpendicular to a line, then I didn't draw the picture right. If it's perpendicular to a line in a plane. So let's put a line in that plane. And let's make our line In other words, we're still coming away from the plane, straight out of the page, straight to your eyeballs. And that is a perpendicular line. Is that line coming out of the plane perpendicular to the plane?
Yeah, the one coming out is.
Yeah, I think it is also. Two lines perpendicular to the same line are parallel. Okay, now we're getting into regular geometry.
Mm-hmm.
This line is perpendicular to that line's perpendicular to that line, therefore those are parallel. It is two-dimensional geometry.
Mm-hmm.
Isn't that the same question?
I don't think they'd put it again.
Yeah, but they did. In a plane, two lines perpendicular to the same line are parallel. If a line is perpendicular to a line in a plane, it is perpendicular to the plane. I guess it's not. No. It's this one. Two lines perpendicular to the same line are parallel.
Yeah, but one has a plane and the other doesn't.
It's true. So the question is, in G, are we restricted to one plane? If we're restricted to one plane, then that is the picture, and the answer is true. If we're restricted to a multiple plane,
That would be false.
correct.
I think it's false because in the other problems, it specifies if it's in a plane.
Yeah, I think you're right.
Yeah, so I think that's false.
I guess.
Yes.
I guess they would be. So what do you call two lines that are parallel that are not in the same plane? In other words, let's say this is a hose, okay, in my backyard. And this is a sticker coming out of the hose. And then I rotate the hose a little bit. And I put a sticker coming out perpendicular like that to the hose. The question is, are these two lines parallel to one another? And I guess they're not, because I think the definition of parallel means they have to be in the same plane. So if you assume that they don't necessarily have to be in the same plane, then no, they're not parallel. All right. A triangle is a plane figure.
That is true because it's just a regular object, not 3D.
It's in one plane, exactly. It's not three-dimensional. A line that is perpendicular to a horizontal line is vertical.
That's false because it didn't say that it was in a plane, on the same plane.
Well, there's a line perpendicular to a horizontal. Oh, I hate these questions. I really do, because yes, that is true. There's a horizontal line, and if I draw a line that's perpendicular to that horizontal line, that is a vertical line. I think that's true, whether they say in the same plane or not. I mean, first of all, when you're talking about vertical and horizontal lines, you are presuming you're in a plane, are you not? I mean, I'm a little confused here, because he is mixing up two-dimensional and three-dimensional geometry. Is your teacher a man or a woman?
A woman.
A woman? In other words, if this was a hose and I had this thing sticking out of it and I rotated the hose, is that still a vertical line? A vertical line only to me has definition in a single plane. In other words, that's a single plane, that's a vertical line. A
Mm-hmm.
vertical line doesn't have any meaning if you're in a different plane. So I don't really know how to answer that.
Mm-hmm.
3 parallel lines must be coplanar, meaning in the same plane. Well, we have the same problem. I don't know. I would say yes, but I suppose that if this one right here was in a different plane than the other, then it would not be a skew line, right? A skew line is neither parallel nor ever intersecting.
Mm-hmm.
I would say that even if you change the plane of that, you still have a parallel line, but I don't know for sure, to be honest with you.
Okay.
Every four-sided figure is a plane figure.
Four-sided, is that on one plane? So that.
Again, I'm going to introduce a four-sided figure to you that is not a plane figure. Picture a playing card. You know what I mean by a playing card?
Yeah.
Now bend it a little bit.
Mm-hmm.
Flex it. Apply your finger and thumb to the top and the bottom and bend it just a little bit so it has a little bit of curvature. It's still a four-sided figure, but it's not a plane. Now, if they would have said four-sided straight, four straight sides, then I would say yes. But if we can have curved sides, it doesn't have to be a plane.
Mm-hmm.
Again, I don't know what he's referring to. So I understand the math and I understand the three-dimensional geometry. I just can't tell by his questions. When he says four-sided, does that mean four straight sides, four straight lines?
Mm-hmm.
Even that wouldn't have to be a plane. If you picture that same playing card, you could leave all four straight lines straight, perfectly straight, and push the middle in a little bit. Just push your thumb on the middle of that playing card, push it in a little bit. You still have four straight sides, but you don't have a plane.
Mm-hmm.
So, I don't know. I mean, I can tell you everything I know. I'm just not sure of what universe he's referring to here.
Mm-hmm.
All right. Let's go down and look at number 2. All right. Given that PB is parallel or perpendicular to the plane M, and PA, line segment PA, is congruent to line segment PC, prove that triangle ABC is isosceles.
Mm-hmm.
Okay. Do you know how to do this, or you want me to start you off?
Since we
Just
know,
walk me through your logic if you think you know how to do it.
we know that angle PBC is 90 degrees.
What else do you know? How about angle PAC and angle PCA? What do you know about those?
Those are acute angles.
They're equal.
Oh, yeah.
In other words, triangle PAC is isosceles. They're
Mm-hmm.
telling us that, which makes those two angles equal.
Mm-hmm.
So that's something else we know. And I believe that's all.
So that would mean that they're 45 degrees.
Well, hold on. Well, we really don't know what this angle right there is in that triangle. So we don't know they're 45 degrees. They're just equal. PB is perpendicular to plane M. PA is congruent to PC, which makes angle PAC equal to angle PCA, but we don't know what it is yet.
So if we know,
Prove this triangle down at the bottom is isosceles. So it would seem to me that we want to prove that AB is congruent to probably AC, right?
mm-hmm.
I mean, certainly from the picture, I would say that that's what we're going to prove. If I can prove that AB is congruent to BC, then that makes that bottom triangle isosceles.
Mm-hmm.
And it seems like we should be able to do that. In other words, if this slanted triangle right there is isosceles, then it would seem that the bottom triangle has to be isosceles as long as that's a vertical line, PB.
Mm-hmm. Yes.
Still we're a ways away from proving it. Let me think about this for a moment. What does it mean about triangle PBC and triangle PAB? Can you picture the two triangles that I'm talking about?
Yeah.
Okay, PAB is the one with the dotted line. That's the back side of that figure.
Mm-hmm.
PBC is the side that we're looking at, the front side, this side right here.
Mm-hmm.
Are those congruent?
I think they should be.
I think they should be also. How can we prove it? I think once we prove that, then we prove that the bottom triangle is isosceles, right?
Mm-hmm.
Because then BC would have to equal AB if
Mm-hmm.
those two triangles are congruent. Well,
Mm-hmm.
let's draw those two triangles. This is P, B, C. And if I draw the back triangle, I'll draw it the same way. That is P, B, A. And clearly that's a right angle, so they're right triangles.
Mm-hmm.
And they've told us that PA is congruent to PC.
Oh, and we know that PB is equal to PB because of reflexive property.
Exactly. So
we have
that's
side
equal
angle
to
side.
that, and in a right triangle, that's all you need.
Mm-hmm.
Is a side and an angle. I forget what the theory is for right triangle congruency, but
Mm-hmm.
those two are congruent.
Yeah.
So if those two are congruent, then it means CB is equal to AB.
To AB. And then we know that that's isosceles because that's the definition of isosceles.
Exactly. So I got off on the wrong foot. We really don't need that. We don't really need that. We want to kind of start there.
Mm-hmm.
In other words, if we can picture this thing properly, if our logic is correct, then our goal is to prove that PBA triangle is congruent to PBC triangle. And once I do that, then I'm proving that. All right. That was a toughie.
Yeah.
You're not in an easy geometry class.
Nope.
All right. In fact, I've tutored probably a dozen honors geometry students, in addition to probably 50 regular geometry students. And this is some of the toughest stuff I've seen. I'm not saying that's bad. It's just, this is not traditional easy geometry, just so you know. Don't get too demoralized if you're not doing great on this stuff.
Yeah.
This stuff gives me a hard time. All right. All right. So given that line segment AB is congruent to AC and angle DAB is congruent to DAC. Oh, wow. So that is congruent to that. Am I interpreting that correctly?
I think you marked BC instead of AC for congruent to.
Thank you. Thank you. Thank you. And then let's see, angle DAB, which is this line here, is congruent to DAC, which is this curve here.
Mm-hmm. Yeah, that part was correct.
Okay. So that's all the information we have. And we're to prove that DB is congruent to DC. Well, given the last problem, what's probably going to be what we need to do here?
We probably need to find the other triangles.
What are we going to need to prove? Which triangles are congruent? In other words, they're asking us to prove that DB is congruent to DC. Well, which two triangles are they in?
DBC.
Okay.
DAB.
So DAB and DBC and DAB are these two front forward triangles that we're looking at.
Mm-hmm.
And if we can prove that they're congruent, then DB would be equal to DC. If I drew them the following way, if I flatten them out, that's D, that's B, that's C, and that's A. You feel me on what I'm doing here?
Yeah.
Okay, I know that's equal to itself.
Mm-hmm. So we know one of the sides. We need to find
Yeah, all the information they've given us is about triangle DAC, which is this back triangle that we can't really see. It's the other side of this triangular pyramid. In other words, there's another triangle involved, DAC, which is this triangle here. I'm going to erase that because it gets to the point where you can't really see what you're doing. That's all the information we have, correct? On the left. Let me draw those two triangles. Let's see if we can prove congruency between those two triangles. A lot of times in geometry, it's helpful to take a picture, whether it's two-dimensional or three-dimensional. I've done it in 2 dimensions all the time, and it's very helpful. You know, sometimes they'll put like 2 triangles in the same picture like that. And what I like to do is take the big triangle out all on its own and then take the little triangle out all on its own. That's a helpful process when they have lots of triangles combined. Well, so let's do it even though we're in 3 dimensions. I'm going to draw a triangle DAC. And then I'm going to draw a triangle DAB. And what I'm told is that DAC is congruent to DAB.
And since we know that DA equals DA because of the reflexive property, that they're congruent because
DA equals DA. But the other piece of information I need is that right there. I need to know that AB is equal to AC, or congruent. And now I have side, angle, side. So I can say that triangle DAC is congruent to triangle DAB. Okay.
And now we know that DB equals DC because it's CP CTC.
And that's all we need. Okay. So in actuality, we never did deal with triangle DBC.
No, we started out on the wrong triangle again.
Yep, you're right. We started out on the wrong foot. I guess the lesson there is take the information they've given you and deal with those 2 triangles right there. DAC and DAB instead of the one I tried to introduce, which was DBC, which was the 3rd triangle and not the one we're interested in. All right. Let's see, do we have any more on this page? I don't think so. How many planes are, well, we got that one. How many planes are determined by a set of 4 non-coplanar points if no 3 of the points are collinear? Are you kidding me?
Well, if they're non-collinear, then it's just 4.
Non-coplanar points. I hate to keep referring back to the same thing, but if we look at a playing card and you push down on this corner in the upper left. You pull up on that corner in the upper right, and you push down a little bit more than you did the other corner there. You pull up a little bit more. Then we have 4 points that are not in the same plane. Agree?
Yes.
Okay. And what's the question? I can't see the whole thing. What's number 4 say?
Number 4, how many planes are determined by a set of 4 non-coplanar points if no 3 points are collinear? I think that's just 4.
How many planes? How many planes are determined by a set of 4 non-coplanar points if no 3 of the points are collinear? So the picture I draw fits, correct?
Yeah.
In other words, when I drew my playing card and I altered the corners, no 3 of those points are on the same line. Collinear means same line. It's not the same as coplanar. If I have 3 points on the same plane, that's different than 3 points on the same line.
Yes.
Well, in my playing card example, I definitely had 4 points that were not collinear, let alone 3. And I had how many planes? I got a feeling there's a stock answer on this and you have to memorize it, and I don't know what it is, and it's really hard for me to visualize it. Let's see if I can do a little bit better visualization. Pushing down on that. That goes in that direction. Pulling up on this, that goes in that direction. Pushing down with half force there, and pulling up with twice the force there. Now I've got 4 points. They're not collinear. How many planes do I have? Well, that's the thing. A point does not determine a plane. Well, you've got one plane that goes between that point, and that point, correct?
Yeah.
In other words, you can always draw a plane between any 3 points, I think. Yeah. I can't picture 3 points in space that cannot be connected by a plane. So that would be one plane. And then I would have a plane between those 3 points. And I would have a plane between those 3 points. And I would have a plane between those 3 points. So I'm thinking the answer is 3. You don't have answers to these, I bet.
No.
Unfortunately. When they're going to ask questions like this, they should give you answers.
Mm-hmm.
Just because it's like calculus. When you take calculus, they always give you not the answers to just the odd ones, but the answers to everyone. Because part of the learning process in calculus is if you don't know how to do the problem, if you know the answer, frequently you can go back and figure out how to do the problem. So having the answer would be useful on this problem here. Just because it's that difficult. At least it is to me. I mean, 3-dimensional geometry has never been particularly my strong suit. It's just much, much tougher than 2-dimensional geometry. Now, some of the standard 3-dimensional geometry shapes that you get like spheres, rectangular bricks, things like that, they're fine. But these problems he's asking here are more abstract than that. All right, let's look at number 5. Is the diagram we're looking at, that's for number 7 only?
Yeah.
Okay. So let's look at number 5. We have a flagpole. Hold on. That is 48 feet in height. Two 60-foot ropes reach 2 points on the ground, each of which is 36 feet from the pole. There's one rope. First of all, is that a proper right triangle? Let's see. I can divide each side by 12, so I have 3, 4, 5. Yeah, that is a 3, 4, 5 triangle. Let's put that dimension right there, so we're not confused. So that indeed is a right triangle. If the ground is level, okay, each of which is 36 feet from the pole, the ground is level, is the pole perpendicular?
Well, if
let's just deal with one of the triangles for the moment. Is that a right angle right there?
Yes.
How do we know?
Because it's
a Pythagorean. In other words, 36 squared plus 48 squared is equal to 60 squared. So if it follows the Pythagorean theorem, not only does a right triangle have to follow the Pythagorean theorem, but the Pythagorean theorem, if it's true, dictates that that's a right angle. Works both ways. Most of these theorems that you're learning all work both ways. Okay? Now, they didn't say that this is all in the same plane. It says the ground is level. So let's draw this one in a little different plane, like this. Well, we know that's 36. We know that's 60. That's still 48. Is that a right triangle?
Yes.
Okay. Because all we really needed was that one. That proves that the... Oh, no, it doesn't. No. In other words, I could make a pole in the ground that was not perpendicular to the ground, that's at a slight angle, and I could still draw a right triangle there, right?
Yeah, you can rotate a right triangle.
If you take a pole that is perpendicular and you push on it so that it's not perpendicular, you'd still have a right triangle. It just, the pole wouldn't be perpendicular. But when you have a second line that also creates a right triangle, then it would be impossible to have two right triangles. If that pole, no, it wouldn't be impossible. What if I have this situation? In other words, this is all in the same plane, okay? So that's 48, that's 60, that's 60, that's 36, that's 36. And let's say you have a perfectly perpendicular pole. Now somebody comes along and pushes on these two triangles at the top of this pole right there so that the pole is not perpendicular anymore. I would still have two right triangles, would I not?
You would, but the pole would not be perpendicular to the ground.
So the only way that the pole has to be perpendicular to the ground is if these two triangles are not in the same plane. I think that you could prove that if this is our picture over here on the upper right,
Mm-hmm.
I think you could prove that if that's not 180 degrees there, and that they're in two different planes, then that pole has to be perpendicular. There's no
Mm-hmm.
way you could take that object and go push on anything. Wouldn't work.
No.
So this is another, what I would call an ambiguous question. He hasn't given us enough information. I guess if he says two 60-foot ropes reach 2 points anywhere on the ground, then no, the pole does not have to be perpendicular.
Mm-hmm.
Even though it seems like it should be, the answer should be yes. Because, I mean, if the answer is yes, then give him this problem right here and say, there's a counter to your proof. Here's a pole that's not perpendicular to the ground, and yet it still satisfies all the other conditions.
Uh-huh.
Wow, these are brutal. Okay. Brutal and a bit ambiguous, I would say.
Mm-hmm.
At a given point on a line, okay, this is one-dimensional. How many lines can be drawn perpendicular to the given line?
At a given point? Would it just be one?
At any given,
Oh.
there's the point on the line. How many lines can be drawn perpendicular to the given line? Again, if you're in one plane, I see only two. But imagine if we're in 3 dimensions, how many lines could be drawn?
3.
Infinite.
Oh, yeah.
Take a hose in your backyard, go stick a needle into a spot on the hose, and where that needle is perpendicular to the hose. And now rotate the hose just a fraction and put another needle on it, perpendicular to the hose.
Mm-hmm.
Can't I put an infinite number of needles on that hose?
Yeah, you could.
If I'm working in 3 dimensions. If I'm working in 2 dimensions, like this, then I can only draw one line. Or if you want to call that a line separate from that, then I can draw 2 lines.
Mm-hmm.
And I don't know what he means, or she means.
Mm-hmm.
Okay, the second part. At a given point on a plane, how many lines can be drawn perpendicular to the plane?
Only one.
I think so. One comes straight out of the page like that.
Mm-hmm.
Unless you want to talk about a different line on the other side of it. In other words, there's also that line there going straight out of the page. But those are the same line, I suppose. So it's just a line that intersects the plane. So I think the answer would be just 1.
Yeah.
Whereas, since they now talk about planes, I have to assume that if they don't mention the word plane, they're dealing in 3 dimensions.
Yeah, so I think the first one would be infinite.
All right. Let's look at number 7. We got about 10 minutes here.
Mm-hmm.
Okay, ADC is x plus 88. ADE is 74 minus 8x. And BDE That's coming out from the other side of the plane.
Mm-hmm.
Well, let's see if we can label some of these on the thing. So this is x plus 88. In other words, what appears to be a right angle is x plus 88.
Yes.
ADE is 74 minus 8x. And BDE, this one right here, is 2x plus 94.
Mm-hmm.
Are AD and M perpendicular?
So if you do, never mind.
So let's see. Can we say that x plus 88 has to be, for that line for AD to be perpendicular to the plane, these angles would have to be equal, I believe.
Mm-hmm.
Certainly looking at it, that would be the case. Not only equal, they would both have to be 90 degrees.
Yes.
Well, so 9x equals negative 14.
I think that's no, because for angle ADC, x has to equal 2. And then obviously for angle AD
Right.
is not equal to.
So there's no way, right. When I tried to solve it, I came up with a negative value for x, which means that ADC is not 90. So no for A. Are AD and CD perpendicular? Well, x would have to be 2, correct?
Yeah, x would have to be 2.
If x is equal to 2, then AD and CD would be perpendicular, but only if x is equal to 2.
Yeah.
Well, what if x is equal to 3? Then they would not be perpendicular.
Mm-hmm.
All right, I think one thing we're ignoring here is this triangle down here. Here, let me. We're ignoring this lower triangle, BDE. That triangle right there.
Yeah.
Now, we don't know much about that triangle, other than that is 2x plus 94. Well, actually,
I think that one just specifically for C.
yeah, that can't be true, right?
Mm-hmm.
Because that means 74 minus 8x would have to equal 90 degrees.
Mm-hmm.
Which means 8x would have to equal minus 16. So x would have to have a negative value.
Mm-hmm.
Now, they don't say anywhere in here that x has to be positive. And they don't say that AB is a continuous straight line. That would also matter.
Mm-hmm.
I don't know. I don't think you can prove any. I may be wrong here, but I think you got no's to all three of these.
I think you could maybe do C because they wouldn't put a triangle, an extra triangle on the bottom for no reason. But I think A and B are no.
The thing is that shape underneath the plane M,
Mm-hmm.
we don't really know much about it. It's not necessarily the same shape as the shape above the plane.
Mm-hmm.
In other words, if we don't know that AB is a straight line, then it could be a curved line like this, could it not?
It could.
And if I can change the positioning of that shape below the plane to whatever I want, then I don't know how we can say AD. Well, it's clear that AD is not perpendicular to that. So I know it's a no on A. I know it's a no on B because AD and CD, that would mean that X would have to be 2.
Yeah.
Well, actually, X could be 2, but we don't know if X is 2. I'm not sure. I think the idea here is we're probably supposed to be able to solve for X. And once we solve for X, then we're going to be able to answer all of these questions. Obviously, if X is 2, then A is true, B is false, and C is false. But only if X were 2. If X were 1, that's why I think we need to consider that lower triangle, because that's going to give us some restrictions on X.
Mm-hmm.
In other words, if AB was a straight line, then I think we could say things like 74 minus 8x would have to be equal to 2x plus 94. But only if we knew that AB was a straight line, and we don't.
Mm-hmm.
And even this would give us what? No, even that gives us a negative x value, which again is not necessarily a bad thing. In fact, if x were negative 2, then that would be 90 degrees. If x were negative 2, that would be 90 degrees. And if x were negative 2, that would be 86 degrees. So you'd have 2 of those 3 that were perpendicular. So all of them are contingent on what x is. If x is 2, then this one is a yes, and the other 2 are no's. But if x were negative 2, then this one is a no, and the other 2 are yeses. The question is, can x be negative 2? I don't know why it wouldn't be able to be a negative number.
Because it
Now,
never specified.
I think I've given you all the thoughts I have on this problem. It seems a little bit ambiguous to me, and the fact that there may be some way we can figure out what x is, whether it's -2 or 2. I don't know. I have to think about it for a while longer. Let me think about this a little bit, and if I have further thoughts on it, I'll get back to you.
Okay.
There may be some relationship between this angle right there and this angle here that I'm not seeing. You know, if this shape down here is supposed to be a reflection of the shape on the other side, but they don't say that either. So it seems to me we don't have quite enough information on this.
Mm-hmm.
Okay? Joseph,
Okay.
I sympathize with you. You're not taking an easy geometry class.
Okay.
This is tough stuff. Eventually you will get into the easy two-dimensional geometry, which is what they should be starting with.
Mm-hmm.
I'll talk to you next time.
Okay. Thank you.
You're